All right, welcome back to another video. In this video, we're going to now look at what we call modified Bernoullis, which involves adding a pump or a turbine or losses from friction into that Bernoulli's equation we've been using. And with that, we need to know what laminar turbulent flow is, Reynolds number, and then we'll analyze a problem. Okay, so let's first talk about laminar and turbulent flow. Inside your pipes at home, you have water moving through it. And depending on the flow rates in diameters and viscosity of that fluid, you can classify that as laminar or turbulent flow. And it's based on what we call a non-dimensional number called Reynolds number. So when you turn your faucet on, typically you don't crank it full blast. So it kind of nice and smooth patterns, and it's kind of clear. This is called laminar flow. When you crank it full blast and it's spinning around and it's going everywhere, this is what we can classify as turbulent flow. There's a lot of circulation in turbulent flow. And actually, a lot of applications, when they need to mix things, they want turbulent flow because it gets everything well mixed. Going from laminar to turbulent, there is a transition region. Okay, and I'll tell you about that. But we're either going to go laminar or turbulent because those are easier equations to analyze. Okay. So right now, laminar flow is smooth, clear. Turbulent flow is cloudy and a lot of circulation. So I'm going to scooch over here and say Reynolds number. Right here. There's an equation that we can use. Sorry, let me put a heading. Reynolds number. It's a non-dimensional number where you have velocity times what we call a diameter or length over your kinematic viscosity. Okay, we can rewrite this as the density times velocity times what we call a hydraulic diameter over mu. So rho is your density, v is your velocity, dH is your hydraulic diameter. And there's an equation for that. It's 4 times the cross-sectional area over the perimeter. This is cross-sectional area, and this is your perimeter. And then nu is your kinematic viscosity, and mu is your dynamic viscosity. Okay, so Reynolds number talks about the differences with what we call inertia, which is velocity over viscous forces. That's kind of what Reynolds number is. And we use it to determine if it's laminar, transition, or turbulent. Okay, and what we do is we use a hydraulic diameter for this D value. And if it's circular pipe, then it's just the diameter of the pipe. Okay, if it's circular. Now, they do make rectangular pipe or ductwork for HVAC systems. And so you just have to kind of know, okay, let's calculate that. All right. So let's define. So if RE is less than or equal to 2300, that's a laminar flow. Okay, that means you're going to get nice, smooth, clear. In between this and Reynolds number, to 4,000, so 2,300 to 4,000. This is the transition. It's kind of where it's transitioning into turbulent. And then when the Reynolds number is greater than or equal to 4,000, it's turbulent. Pretty much, we kind of avoid the transition region because it's really hard to analyze that over the years. We have equations for laminar and turbulent. And so we're going to go with one of those. All right. So we've talked about what laminar flow looks like. We talked about what turbulent flow looks like. We're using a Reynolds number, which is a non-dimensional, which deals with like inertia, velocity over viscous forces to determine if it's laminar or turbulent. And the next thing is we can now kind of utilize all of that with a modified Bernoulli's equation to calculate what we need to move this liquid in a pipe. Okay, so let's talk right here, and we'll do the practice problem after. Modified Bernoulli's equation. All right, so I'm going to write the Bernoulli's. So P1 over rho G. I'm going to write each term in terms of head. V1 squared over 2G plus Z1. And then I'm going to leave a space, and then I'm going to put this over here. P2 over rho G plus V2 squared over 2G plus Z2. I'm doing that on purpose because we're going to add 3 terms to the modified Bernoulli's, or to the Bernoulli's to make it modified. The first one is HP. This is head from a pump. So if we put a pump in line to move liquid, or gas, or liquid is typically a pump, okay? We'll talk about pumps, fans, and stuff later. We add energy to the system. We're adding it, okay? If we have a turbine, we subtract energy. So this is turbine, okay? Because it takes energy away from the system. And then you also have losses from friction. Okay, so this is the modified Bernoulli's equation that incorporates now like pump, a turbine, and losses, and we can use this now to get a much more accurate solution of how much power we need to overcome losses in a pipe and what we call minor losses, which I'll talk about next time, from elbows to valves to constrictions and whatnot. Okay. So if you have a pipe, this is P1, this is P2, you have your hydraulic diameter, this is the length. The friction loss, HL, is given by this formula. F times L over DH times V squared over 2G. Okay? And if it's laminar, that's what we're going to look at now, then for a circular pipe, the equation is 64 over the Reynolds number. Okay. Now, there are other equations for a rectangle pipe. You can find those in the book, but right now we're just going to do circular pipe. Okay. So you can find the losses by this equation. It's pretty cool. The F, it's just 64 over the Reynolds number, only if it's laminar flow. L is the length of your pipe. DH is your hydraulic diameter. So if it's a circular, then it's just D. V is your velocity of the liquid. and then g is your acceleration due to gravity. So we have HL now, and most of the time we're either going to calculate maybe the power of the pump. So we're going to calculate HP, or we're going to find it. Okay. So let's do a practice problem so you get an idea of how all of this combines. Okay. One last thing I want to give you before we do that, I forgot, is the power. So if we want to know the power to move liquid in a pipe, W dot, you need to know your volumetric flow rate and your delta P. Okay. Delta P, we're going to find from the modified Bernoulli's. So, and that modified Bernoulli's now has what? Pump, could have a pump, could have a turbine, or those losses. Okay, cool. All right, so let's go do this practice problem. Consider a flow of oil with rho equal to 894 kilogram per meter cubed and mu 2.33 kilogram meter second in a 20 centimeter diameter pipeline at an average velocity of 0.5 meters per second. A 330 meter long section of pipeline passes through the icy waters of the lake. Determine the pumping power required to overcome the pressure losses and to maintain flow in the oil. So just to give you a reference, or like this is rho and this is mu. Okay. So given we have rho 894 kilogram per meter cubed. We have mu 2.33 kilogram per meter second. We have the diameter, which is 0.28 meters. We have V, which is your V average, 0.5 meters per second. I believe L, 330 meters. We're looking for that pumping power, W. Assumptions. We got steady state, incompressible. Here's our sketch. Basically, we have a pipe. We have a diameter D. We have 0.1, we have 0.2. This is L. And we should be good now where we have given, find, assumptions, sketch. We can now write the solution and start calculations. Oh, sorry. Let me undo that. There we go. Solution. We're going to write the modified Bernoulli's. Which is P1 over rho G plus V1 squared over 2G plus Z1 plus HP minus HT minus HL equals P2 over rho G plus V2 squared over 2G plus Z2. Now, important we draw our sketch and our labels. So we're going to go back to the sketch. And the velocity is the same. From 1 to 2. Let's look right at the center line. Okay. So those two go away because those are the same velocities and it's a pipe. Okay. We're going to do the center line. So the velocities are the same. There's no elevation change between Z1 and Z2. Is there a pump or a turbine? Nope. So we end up getting HL equals, we get delta P is rho G times HL after I rearrange. Okay. So I multiplied every term by rho G. And so it's P2 minus P1. Oh, nope. Bring that over. Sorry. P1 minus P2, which makes sense. In a pipe, the pressure here has to be greater than the pressure 2. That's how you get flow. Okay, this direction to the right. So P1's got to be higher than P2. Cool. All right, so we use the modified Bernoulli's. We solve for delta P. Now we can find HL. And HL we said was F times L times V squared over 2dg. All right, we need to find F. F equals 64 over the Reynolds number. Okay, we need to find a Reynolds number. Reynolds number equals rho VD over mu. So let's go ahead and plug that in. 809. So the Reynolds number equals 894 kilogram per meter cubed times 0.5 meters per second. What was my diameter? 0.28 times 0.28 meters over 2.33 kilogram per meter second. Get a Reynolds number of 54, which is laminar. That's a good check. And then now F becomes 64 over 54. F becomes 1.19. Now we can plug that in. HL is 1.19 times 330 meters times 0.5 meters, and this is squared, all over, how did I write it? 2 first? Yep, 2gg. 2 times the diameter, which is 0.28 meters times 9.81 meters per second squared. Our losses from the pipe, 17.9 meters. Okay. And then now we can find delta P, which is delta P equals 894 kilograms per meter cubed times, what was it? Rho GHL. Rho G, 9.81 meters per second squared times 17.9 meters. Delta P is 157 kilopascals. So that is P1 minus P2. Okay, so that's the change in pressure to keep this flow from moving at constant speed because of friction. Okay, and then now we can calculate the power required, which is V dot times delta P. W dot is A times V times delta P because we didn't give the flow rate. And the area is pi d squared over 4 times the velocity times delta P. And now we can break it down. 0.28 meters squared over 4 times 0.5 meters per second times 157 kilopascals. So the pumping power is 4.8 kilowatts. So you need almost 5 kilowatts of power to move this liquid, this oil, at 0.5 meters per second in this pipe. Okay, to keep it constant speed. All right, so this is a practice problem where we're dealing with laminar flow, and it's overcoming friction to keep the liquid moving at constant speed. Okay, we had to use the modified Bernoulli's and this new term Reynolds number, and this new term of with this major loss. So HL is what we call a major loss in pipes, which overcomes the friction on the outside of the pipe. All right, so again, recap. This talked about laminar turbulent flow. We introduced Reynolds number. I showed you the modified Bernoulli's. And then we did a practice problem involving laminar flow to calculate the power required to keep it moving, to keep the liquid moving at constant speed. Next video, we'll be doing turbulent flow. And the equation for F is different. You have to either use an equation or a chart. All right, thank you, and good luck.